Hi everyone, welcome back. It's been a while since I made a video, so I do apologise about that. Life has been very hectic, very busy. Hopefully I'll get the chance to make some more in the next week or two. Okay, so what we're going to look at today is we're going to start off with elements, compounds and mixtures. So we're looking at topic 1 for all of the sciences. It's atomic structure in the periodic table, and we're looking at part 1 of that because there's 2 parts of this, and we're looking at atoms, elements and compounds. And today what we're going to do is have a very quick discussion on what the differences between elements, compounds and mixtures are, and how we can do those in diagrams. I'm going to have a look at what the real definition of a chemical reaction is, as opposed to the one that you might have learnt at Key Stage 3. And if you have not been taught by me at Key Stage 3, you might have learnt that a chemical reaction is a reaction that is irreversible, and a physical reaction is one that is easily reversed. This is not true. It is not good enough as a definition. It's just completely wrong. So I don't teach that, and I'll teach you a better definition, a more accurate one. Then we're going to have a look at some other ways that we can separate mixtures and be able to decide on suitable methods of separations. Okay, different examples. So this is something that the syllabus requires you to be able to do for the exam. So, elements, all found on the periodic table, we've found here. So every last element that, as far as we know, and we're pretty sure that every last element in the entire universe is on this periodic table. Some of them are very few when you start to get to like the bottom end here. Some of them are artificial. They have to be made in a nuclear reaction or in a particle accelerator, but most of them can be found naturally as products of stars, essentially. So when people say everyone is stardust, this is why. It's because when a star explodes, it creates all the elements that are on the periodic table. Okay, literally everything in the universe, apart from maybe if you're going to argue about plasmas, is made from one of these elements in one form or another, or a combination of several of these elements, including the air you breathe, literally everything. Okay, at the moment, a little bit of interest, about 118 elements have been discovered so far. You don't have to necessarily know the exact number, but you have to know that around 100 elements have been discovered. Okay, and that's how many are on the periodic table. And you should be able to figure out that most of them, if you have a look at the periodic table, most of them are metals. So most of the elements are metals. There are only 2 that are liquids at room temperature, and they are bromine and mercury. Bromine being a halogen in group 7, and mercury being a transition metal, or a metal. And you probably know of mercury already. Of all the elements of the 118, only 10 are gases. The rest are solids. Okay, so 2 liquids, 10 gases. The rest of them, 106 of them, are solid. Each symbol on the periodic table represents an element. For example, O is oxygen, C is for carbon, and Pb is for lead. So if we go back to the periodic table, here we can see all of these symbols represent a different element. So these are all our different elements. O for oxygen, C for carbon, Pb, where is it, down there, for lead. Okay, so all represented by symbols, and this is so scientists can communicate very easily with each other. Okay. Another thing is that the names of the elements are all just one word, and we've got some examples there: oxygen, carbon, lead. You can go through the periodic table and have a look yourself and see if you can find any that don't fit that pattern. But for example, plutonium, uranium, lithium, all one word. Now, the symbols. So some things we need to know about the symbols, because the symbols, chemical symbols, they make such a big difference to all of chemistry. So the symbol will always start with a capital letter. Always, without a shadow of a doubt, it will start with a capital letter. If it has a second letter, or a third letter in some of them, these are always lowercase. So you can always tell the start of an element in a compound because it always starts with a capital letter. Okay, so we've got 7 little things there. 1, 2, 3, 4, 5, 6, 7. Give yourself about 60 seconds. You shouldn't need any more than that. And go through those and work out which of those is just one element and which of those is more than one element. And you can put the video on pause and I'll give you the answers in a second. Okay, so first one, N, just one, nitrogen. Second one, Fe. We've got a capital letter and then a lowercase letter, so that is just one element, iron. 3, we've got a capital C with a lowercase o, so that's cobalt. 4, however, we've got a capital C and a capital O, so we've got carbon and oxygen, so this is carbon monoxide. This is not just one element. Part number 5 is H capital, F capital. So that again is not just one element, it's two elements there, so that is not just one element. 6, capital A, lowercase u, that is one element because we've just got one capital letter in there. And then we get 7, we get O2, so we've only got one capital letter, oxygen. Oxygen gas always goes around in a pair, and so therefore that's an element. Okay, so little definition of an element. An element is a pure substance made from only one type of atom, and they're all found on the periodic table. So there is what elemental sodium would look like. So metal, sodium metal, it's just sodium atoms. Oxygen there, okay, we've got 3 oxygen molecules made up of 2 oxygen atoms joined together. It's an element because there is only oxygen in there. And then lastly, nitrogen. Okay, so there we go, we've got 2 nitrogens joined together, but because we've only got the one type of atom in there, it is an element. You should be able to draw these diagrams out and be able to draw them for any given atom on the periodic table, any given element, but the idea is if it's an element, it's just got the one type of atom. Compounds now. A compound is made from 2 or more different elements that have been chemically joined together. So they have to be chemically joined together. And they are formed from elements in a chemical reaction. And you can often tell when a chemical reaction has happened because you get detectable energy change. And this again is coming from the syllabus. It's something that they want you to know. For example, it will give off like heat or light. Okay, and we'll be doing more on those in topic 4, energy changes. Chemical reaction, and here is our new definition, is not something that is irreversible or hard to change back, because there are quite a lot of chemical reactions that change back very readily. So it's a bad definition. But a better definition is a chemical reaction is a process that involves the rearrangement of atoms and it makes something new. Okay, so the reactants, what you start with, are going to be different chemically from the products. They're going to be rearranged in some way. So just like elements, compounds will have formulas, okay, made up of the element symbols, and those symbols for the formula will be just the elements that go up to make that compound. For example, carbon monoxide, we've got 1 carbon, capital C, 1 oxygen, capital O. Copper oxide is copper, capital C, lowercase u for copper, capital O, oxygen. Okay, now most compounds have more than one word in their name as well. So for example, we get carbon dioxide, carbon monoxide, copper oxide, iron sulfate, hydrochloric acid. There are some examples which don't follow this rule. For example, water, but that's a common name for water, and we'd often call water, what we might call water, dihydrogen monoxide. Another example of a compound that has a one-word name is methane. Okay, but they're things that you're going to know, have to learn. Okay, and ammonia as well. Now, a molecule is a group of elements that are chemically joined together. They can be the same or they can be different. Okay, these elements, as I said, if they're the same, you'll get something written like this: O2. That means we've got 2 oxygen atoms joined together. S8. Can you guess how many sulfur atoms are joined together? Yep, it's 8. And then we get Cl2. Okay, for example, carrying on. In a compound's formula, we're always going to have a capital letter at the start of it. Okay, if it's a small number after a capital letter, it means, or an element, it means there are that number of that element in the compound. For example, here we've got CO2, carbon, capital C, O, oxygen, capital O, and we've got a 2 after it. Okay, because there's no number after the C, we imagine there's a little 1 hiding in there. Okay, that tells us we've got 1 carbon. There's no point in writing it, it just saves time. We have a small number 2 after the oxygen. Okay, and this number 2 refers to the letter or the element that it follows immediately. Okay, so it doesn't refer to two carbons. We don't have two carbons. We've got two oxygens. So carbon dioxide, we've got one carbon, two oxygens. Another example, slightly trickier, H2SO4. Give yourself 30 seconds, see if you can work that out. Okay, so first step, if you didn't get it, if you were unsure, is we have to identify which elements we have. Now we've got a capital H, so hydrogen, capital S, sulfur, and a capital O, oxygen. Step 2, we check for the small numbers after them, and we can see we have a 2 after the H, no number after the S, and 4 after the oxygen. So that means we've got 2 hydrogens, 1 sulfur, and 4 oxygens in H2SO4, which is sulfuric acid. Now, if you have a big number to the left of the formula, then it means that we're going to have that many of the entire compound. For example, if we had 2 H2SO4, it'd mean we'd have 2 lots of this, so we'd have 2 times everything that's inside it. So that means in this example here, for the 2 H2SO4, we'd have 2 times 2 hydrogens, 4 hydrogens, 2 times 1 sulfurs, 2 sulfurs, 2 times 4 oxygens, 8 oxygens. If we had 7 H2O, that would mean we have 7 H2O molecules. So we'd have 7 times 2 hydrogens, which is 14, 7 times 1 oxygen, 7 oxygens. So, definition that you need to know. A compound is a substance made from 2 or more atoms of different elements bonded together. Okay, so different exclamation mark there because it's something that we need to be aware of. So compound is different elements bonded together. And here we've got our example of water. Oxygen, hydrogen, hydrogen, oxygen, hydrogen, hydrogen. You can see this is different from a molecule because we have more than one type of atom. Okay, carbon dioxide, and then this last one is called methane. Okay, so here we've got carbon and hydrogens joined together. Now we can put these things, the equations, into a symbol equation. Okay, so symbol equations are useful because it can tell us how many molecules of a substance are going to react to give a new substance. This is useful for industry, saves money, saves us wasting products, saves the environment. The thing that is going to do the reacting, which is going to be on the left hand side of the chemical equation, is called a reactant. The thing that gets made on the right hand side of the arrow is called the product. And here is an example. So we've got a word equation at first. Hydrogen plus oxygen, arrow, water. Okay, so that means hydrogen and oxygen react together to make water. Hydrogen and oxygen are our reactants, water is our product, and here is our symbol equation. 2H2 plus O2 makes 2H2O. Now you'll notice I've put big numbers in front of here. I can't just write H2 plus O2 arrow H2O. Okay, it's got to be balanced. We've got to have the same numbers on each side. And I will put a link in the description below. I have a video on how to balance equations as well, which is a really important skill in chemistry. It's one of the most important things for GCSE Chemistry. Okay, now a mixture, last thing here. So we've looked at elements, we've looked at compounds, we've looked at molecules, so now we're going to look at mixtures. Mixtures are where we have 2 or more substances, and these could be elements, they could be compounds, that are mixed together but are not chemically joined. And an example might be salt and sand if you mix those together, or if you've got different colours of Skittles in the bag of Skittles, that's again a good example of a mixture. One that often doesn't get thought about is if you look around you at the air. The air is a mixture. It contains oxygen, nitrogen, and a small amount of other gases. It's about 21% oxygen, 78% nitrogen, and 1% other gases. And another good example of a mixture is seawater. And you might be able to have a think about some of the things that might be in seawater. There's obviously water. And we get the salt, which is what tastes awful. But then you get little bits of plankton, probably bits of plastic nowadays, and various other things that are dissolved into the water. So we have here 4 different mixtures. We've got a mixture of nitrogen and oxygen, a mixture of carbon dioxide and carbon monoxide. You'll notice this is very similar, but this top one here, we've got a carbon bonded to 2 oxygens, carbon dioxide, and we've got a carbon bonded to 1 oxygen down here, carbon monoxide. So they're different compounds, so they are a mixture. Here we've got a mixture of 3 different compounds. We've got nitrogen dioxide, we've got carbon monoxide, and we've got water. And here we've got a mixture of 2 hydrocarbons, which is topic 7, I think. So something to come on to later. Okay, so 2 elements, 2 compounds, 3 compounds, 2 compounds. Okay, and again you should be able to draw a diagram of a mixture, or recognize as well from a diagram what a mixture is. Now for the interesting part, separating mixtures. You've already probably got a good idea of how to do this in a kind of a kitchen chemistry kind of way. And what we can do is we can separate substances in a mixture by using their physical properties. For example, their size, their boiling point, solubilities, and things like this. And you are expected to know this. One example, and it's not chemistry per se, but we can separate marbles from sand by sieving them. You can probably work out why that happens. How can we separate marbles from sand? By using a sieve. The same thing, how can we separate rice and pasta using a colander? And if you're unaware, a colander is one of those big metal things that got big holes in it, as opposed to a sieve, which has got really, really fine holes. And those two obviously work because the holes in the sieve and the holes in the colander allow either the rice or the sand to fall through whilst trapping the marbles or the pasta. Now, there are 4 methods you need to know for GCSE chemistry of separation, and these are filtration, crystallization, distillation. There's 2 types of distillation there, simple and fractional, and then the last one is chromatography. And you've probably had a go at some of these already, but not called them by necessarily those names. None of them involve chemical reactions. They involve physical reactions, they involve melting things, they involve boiling things, they involve evaporation, they involve the sizes of things, but they don't involve a chemical reaction. So first up, filtration. Filtration, little definition or simple definition, is it can separate insoluble solids from a soluble liquid. For example, if you've got sand in water, you can separate those. Okay, so you can separate sand from the water by putting it through filter paper. The sand gets trapped. Now the example I've got here is if you had salt water, for example seawater with sand in there, and you put that through the filter paper, the sand would get trapped, but the salt, because it's dissolved, would pass through. And you should have had a go at this, and basically what you do is you get a paper cone, filter paper, make a cone, put it into a filter funnel. It's important there, you need that to hold the filter paper, and you carefully pour your mixture in to the filter paper so it doesn't flow over the top. What happens is the insoluble solid, which gets called the residue, gets left behind in the filter paper because it can't pass through. But the liquid, which gets called the filtrate, will pass through to the container at the bottom. That might be a conical flask or a beaker, and that's because the filter paper's got tiny little microscopic holes in. The sand cannot fit through, but the liquid can. Okay, and that means the solid gets trapped, the liquid pours through. If you need to get the residue dry, and I have seen this come up in an exam question, how do you get dry sand from a salt water mixture? Then you can dry it. Okay, heat it, put it in an oven, put it in a warm place, and dry it off. Okay, just like you'd dry a pair of clothes. Next method, crystallization. Crystallization is a process which separates soluble solid from the liquid it's dissolved in, but you lose the liquid. You get the solid that's dissolved in something, but you lose the liquid. For example, you can get crystals of copper sulfate from a solution of copper sulfate, and you might have tried this. It's a good primary school experiment. I remember doing it in primary school anyway. And you get some copper sulfate, you get a little crystal, you tie a little bit of string around it, and you dump it into a saturated solution of copper sulfate, and you leave it for the copper sulfate solution to evaporate, and it creates or leaves behind the copper sulfate solid. Okay, so copper sulfate dissolves in water to make a solution, but if you evaporate the water off, it forms a solid again. Now in chemistry, what we often do is we use something called an evaporating basin. It's like porcelain basin, little dish. It looks like a small breakfast bowl, cereal bowl. So you pour your liquid into there. Then you can heat it gently over a Bunsen burner to evaporate off some of the liquid. Then you can turn off the heat and leave it uncovered in a warm place for the rest of the solvent to evaporate. So have a little think about why why do we have to leave it uncovered? And you might have worked out that we leave it uncovered so the liquid can evaporate off. Otherwise, if we put a lid on it, it'd get trapped in there and it would never evaporate. Okay. The slower the process, okay, the longer we leave the liquid to evaporate for, the bigger the crystals you make. So if you want to make some big crystals, you leave it to evaporate slowly. Now, simple distillation is useful for separating a liquid from something that is dissolved in it, okay, and this time we get to keep the liquid and the solid. And a good way of using this would be to get pure water from salt water. So if you were stranded on a desert island surrounded by the sea and you only had a few bits of driftwood, you could make yourself a pure water by distillation. The reason why distillation works, both types of distillation, simple and fractional, is because of a difference in boiling point. And what you'll need to do for simple distillation is you heat the mixture to boil the solvent. The solvent vapors will then travel up and then into a condenser tube, which cools the vapors back down so they condense into a liquid, and then you capture it. And we'll look at a diagram in a minute. It's very similar to this diagram. Fractional distillation is used for when we need to separate one liquid from another. This is quite a difficult process. You get to keep both of the separate liquids, and one big use of it is to get alcohol from alcohol and water, so we can ferment something, whatever that might be, potatoes, grain, and get a weak alcohol solution of maybe about 14%, and then you can distill it up to get it up to 50, 60, 70, 80, 100% alcohol. So it works because of a difference in boiling point, and what happens is you heat the mixture to boil the liquid with the lowest boiling point. Okay, so the one that's got the lowest boiling point, for example, if you've got alcohol and water, alcohol boils at about 78 degrees Celsius, so you heat the liquid to 78 degrees Celsius and the alcohol will boil off, but not the water. The vapors will then travel up, the alcohol vapors will then travel up your reaction vessel, which I'll show you a picture of in a second, and then down into a condenser tube. As it goes down that condenser tube, that cools the vapors back down so they condense into a liquid, and then we can stop heating the reaction when the temperature starts to rise again, because that means we've boiled off all of the first liquid. And this is what a fractional distillation, and indeed a simple distillation tube, would look like. Okay, so we've got a round bottom flask which we put in our mixture of liquids that we're trying to separate. Sorry about that. We heat it up with a Bunsen burner over a tripod. We have a thermometer in the top of this tube here. Notice that the bulb of the thermometer is about level with this arm that comes off down here. So this bit here is the condenser, and this bit here is our pure water or pure alcohol, whatever boils first. And the condenser tube, you'll notice if you look really carefully, has got like a tube which runs all the way down the middle, and it's surrounded by a jacket. And what happens with that jacket is we pump cold water in at the bottom, and the cold water runs its way up to the top, then comes out down this tube and into a sink, and this means all the hot vapors that are coming down here get cooled down, so they turn into a liquid and then drop off into this. So you are expected to be able to draw this diagram for the exam. You will be expected to label it up and name all the parts as well. So I'll just go through this again nice and slowly. If you want to draw this out before I go through it and give each part, then put the video on pause now until you've done that. So firstly, we've obviously got a Bunsen burner, but you don't have to use a Bunsen burner. You could just use an arrow which says heat, okay, a big arrow that says heat. This would be particularly useful if you were heating alcohols or other things that were flammable. In that case, what you might want to use is a water bath or an electric heater, and again, that's something I have seen come up in an exam question. So what's going to happen is then your mixture here in your round bottom flask is going to evaporate. Okay, the vapours will rise up this column. Now in fractional distillation this column will be much larger, it'll be much taller. Here we have our thermometer, and note the thermometer's position is at the same level as this neck here. Very important that you make sure you get that. This bit here is called the condenser tube or Liebig condenser. Okay, so this is our condenser, and this here would be our distillate. Okay, like our filtrate, our distillate, the thing that we've made, pure water, pure alcohol, whatever it might be. It's also important to note that the cold water goes in at the bottom of the condenser tube, and the hotter water comes out and goes back into the sink at the top of the condenser. Well done, guys. Okay, a little summary now then. So elements are found on the periodic table. Each element has the symbol that starts with a capital letter, and any other letter in a element's symbol must be a lowercase. Compounds are two or more elements that are chemically joined, and again they have their own chemical formulas, the compounds, which will contain all the symbols of all the elements that make it up. Mixtures are different substances mixed together but not chemically joined, and we can separate mixtures using separation techniques which separate the substances in the mixture based on the physical properties of those individual substances. Right, I'll leave you with a joke. Why should you never trust an atom? Because they make up everything. I'm here all day. Okay, take care guys. I hope you found this useful for revision or for learning while we're distance learning, stuff like that. I hope to see you around soon. Okay, bye bye.